Okay, thank you guys. Always a pleasure to speak here. Feels like family. So, if there's anything I'd like you to take from this talk today is that there is an ancient, like 40 years old transaction processing and SQL technologies that keeps coming up in the AI scenarios we see on a daily basis in our companies. So maybe that would be the most important takeaway, and the stories around the system that we built mostly here in Haifa with my colleagues Oad Chacham and Jonathan Gottsman, and successfully applied to many products in multiple products in production. The new kind of workload that we are going to describe is called Translytics. So what is Translytics? It's a comparatively new new concept, so which kind of combines transaction processing with analytics. So we'll devote just a bit of time of describing the use cases and why do they reach the cloud scale. How we do that in the world of big data technologies revolving around the HBase, Omid, and Phoenix triangle, and maybe we'll have some time to dive a little bit deeper into these technologies. So to start with, when AI or ML-based applications started off like 10, maybe a little bit more years ago with big data for real, most processing patterns were inherently batch-oriented, which means that you bring your data in, you train your models, and then you apply all the inference mechanisms in the real time. So this no more applies in many scenarios these days. So in fact, I just made a quick search in the internet and brought this survey in which many companies across many different domains have been asked what kinds of real-time analytics do they use in their environments, and the trend is very clear. People keep training. Their models keep extracting data in the real time. So as the data arrives, there is a lot of processing that updates these machine learning models, deploys them for serving, and keeps them hot within very short delays, minutes to seconds, in fact. So all this gives a very clear push to a very different set of technologies. So if 5 years ago, 10 years ago, Hadoop was king because it could handle huge amounts of data in a batch setting, run jobs with 1,000 tasks or more, running on huge amounts of data. Right now, the data is arriving in the real time, and the push is very clear towards stream-oriented technologies. So, from the application perspectives, what we see is that while in batch processing bandwidth was king, in this context, event to action or insight latency becomes king. As we said, stream processing technologies become prevalent, and what is more important is that we as application developers no more have control over the execution timing. So many events that are processed in real time occur at random timing and in parallel. So having the big pool of data shared and being updated concurrently makes the data consistency issues non-trivial. So all that belongs to the old OLTP world, online transaction processing world, that we all know from banking and financial applications. And you might say, oh, all that doubt. People solved these problems 40 years ago. Why should we deal with that? So the reason that we come back to all these scenarios, that the kind of processing we need now is much more complex, with a range of scenarios, right, ranging all the way from the simple online dashboards to AI, and the need to aggregate across multiple feeds as schemas in a very consistent way. So Translytics is nothing but just a buzzword. There are other buzzwords for the same concept, but it's basically a marriage of OLTP and complex analytics in order to enable complex, consistent, and real-time processing. And the gist of it is actually providing a very simple API backed by strong guarantees. So the idea is when we take a step back and look at the evolution of the big data systems, is that we want to build on top of the very nice scaling capabilities of big data platforms, but like age-based key value stores, for example, but build to build stronger and richer semantics on top of them. So what are we short of in traditional NoSQL? So in traditional NoSQL, the data schema is really done. You have your view of the world is a huge collection of key value pairs that are called rows for this matter, and the traditional NoSQL access only guarantees row level atomicity. So it often happens that transactional AI applications need more than that. They need atomic accesses to multiple rows. And what makes it worse is that asynchronous design patterns, when stuff arrives out of order, drives a lot of concurrency. So without the standard ACID guarantees, chaos really rules. So let me give you a couple of examples. Our use of these transactional technologies started with online indexing of the web. This is an application that has been running in production for something like 5 or 6 years. And a more modern example comes actually from the computational advertising world. So in ad tech, what happens is that when a marketer defines an advertising campaign, the super important part of it is which audiences, user audiences, are picked to target in this campaign. So in order to make the marketer's life easier, the population of these users that come with the internet traffic is split into really big chunks that are called segments. Okay, so the quality of these segments and the speed at which these segments are built and the users are classified to them is actually the competitive edge of the advertising engines that they when they compete with each other. So the ad tech platforms actually build and sell these segment data to advertisers based on their own unique data that they drive from multiple sources. So this segmentation is actually based on user features like age, gender, geography, all kinds of behavioral features, etc. And the algorithms applied during this classification, they may vary from rule-based heuristics to AI classification, and really timeliness is very closely linked to revenue. The faster you track a single event and classify a user to a particular audience, the higher your revenue goes up. So just a bunch of buzzwords to throw in here. The technologies that we're using for this real-time processing pipeline is Apache Storm, which is a stream processing technology. Actually, if you compare the Storm to technologies like Spark or Hadoop, you have a multitude of tasks, but in contrast with the batch tasks, they don't run for a limited round of time. They are just like services that stick around persistently and keep processing the data as it goes in. So a Storm job is typically named a topology, and a typical topology in our setting can have hundreds to thousands nodes. So all these jobs actually share the same data pool, which stores their users' characteristics, and for this we use Apache HBase, and Kafka is a messaging substrate that actually glues all these processing elements with each other. So when you imagine a processing pipeline that we use, it's multiple stages of Storm jobs that store intermediate results in HBase. So the input to this whole system comes from multiple feeds, and the output goes to searchable indexes that are streamed to the runtime serving platforms. And we are speaking here of about trillions of new data points that are processed each month. So our challenge in this context is keeping the data persistent. So the problem is obviously a standard problem in distributed computing. You have multiple processes that touch the shared data. There is no, in a sense, data affinity. So a single user's events might be processed by multiple parts of these topology, multiple processes. They might access the same record in the same time. Moreover, a single event might be split around multiple processes because, for example, a user is classified to segments through up to 5,000 different models and pattern filters. So in order to not create any bottlenecks, a single event is broadcast to multiple bots that might end up updating the same record. So the access patterns are complex. For example, a single user profile update might or might not end up by a write to the database. There are mutual references between users and segments in which we use. There are two writes and that have to happen atomically. When we run an online scan, we want to get a consistent view of the database when running multiple rows. So HBase, the HBase API doesn't provide anything of that. So here, Omid, the project we worked on for 5 years, comes to help. So actually, this is a transaction processing layer on top of Apache HBase. It's an Apache project that is graduating the Apache incubation. It has a very easy to use API. It has a very popular consistency model that is called snapshot isolation. It's very similar to serializability of normal transactions, but the implementation is much faster, and it's been in production for almost 5 years from now. So in order to convince you that the API is really simple, so this is this is an example of a sample HBase program, and the parts that are in red are actually what we pad with the Omid code. So as you see, we just need to frame a piece of code between the begin and the commit of the transactions, and all the API calls are just padded with this new transaction ID that we get at the beginning. The rest of the runtime system does all the logic behind the scenes. Okay, we'll have a chance to come a little bit to the to Omid's performance down the road. So one more thing that is happening is the integration between SQL and NoSQL system. The problem with NoSQL is that it's very crude and it is non-standardized. Like, you have multiple vendors. There is a conceptual common ground between the APIs, but there is really no compatibility. It's hard to manage complex schemas. It's hard to implement analytics queries. It's really hard to optimize for speed, because traditional databases do a lot of server-side optimizations that are close to the data, and it's really hard to do this kind of stuff with NoSQL databases. And moreover, it's hard to integrate with the relational data sources. So one more example from our experience is real-time ad inventory ingestion. So in our industry, inventory means all the campaign definitions, the creatives, the metadata, the audience targeting information, etc., that advertisers deploy when defining the campaign in the marketplace. Now, on the one hand, the campaign operators, the guy that look after the campaign and see that the budget gets spent wisely, they on the one hand they want to use multi-dimensional inventory analytics, and for that they want to use their familiar SQL tools. And on the other hand, we want to be capable of running all those data pipelines that used to have NoSQL access over HBase for that. So a new project called Apache Phoenix comes to help here. So it's actually a SQL skin on top of HBase that provides both OLTP and real-time analytics on top of HBase. It uses a very mature query optimizer that transforms SQL into native API calls. Very simple JDBC compatible SQL interface, convenient mechanisms like secondary indexes, and a lot of applications that make the developers' life much easier, like using the HBase capabilities of running server-side code really close to data, something that can increase the performance a lot, but is really hard to program. So Phoenix does all that. So a recent project that we are actually very proud of is that we have just finished the integration of Omid as the transaction processing backend in Phoenix. So this system is publicly available. It's designed to be to work at the public cloud scale, like running on clusters of more than 10,000 machines. It can run a load of more than 600,000 transactions per second. So if you divide this by that, that means that every single machine would be producing tens of transactions every second. Very low latency and high availability. So all of that developed here in house. So just in order to conclude and to show the way that we made since the first version of Omid that has been deployed in the field. You can see that the first version of Omid could scale quite nicely to hundreds of thousands of transactions per second. However, it hit the performance wall because of the specific protocol, around 200,000 transactions per second, the overhead just became unbearable. Now the new protocol that we've implemented in Omid recently stays flat as we scale. So just finishing up, the AI world is marching towards real-time processing. I hope that I convinced you that streaming, messaging, KV stores, and transactions are now the necessary tool set for AI developers. You learn a new word in Persian, Omid, which means hope. The guy who actually started the project was Iranian by origin. And one more new buzzword is Apache Phoenix is a SQL paradigm for AI. Thank you.